Hello everyone. It is my great pleasure today to talk to you about our recent work on distilling massive multilingual models. My name is Shubhabrata Mukherjee. This is a joint work with Ahmed Hassan at Microsoft Research. In recent times, language model pre-training has been adopted for a number of natural language understanding tasks where they have shown superior performance. In this, deep and huge neural networks are trained on large amounts of unlabeled data with self-supervision objectives. Thereafter, the representations are fine-tuned on task-specific labeled data for the downstream tasks. With this principle, a number of language models have been developed, ranging from BERT, GPT, and our in-house Turing NNG. While these models have been successful in obtaining superior performance for so many tasks, their huge models are a concern to use them in practice. For instance, the most recently released GPT-3 boasts of a massive 175 billion parameters. Prior works in the vision community has addressed this shortcoming using a technique called knowledge distillation. The objective here is as follows. You have the teacher model, which is the huge pre-trained model, and we want to transfer the knowledge to a shallow student model. The knowledge transfer takes place over unlabeled data, which acts as the transfer set. Now we can use the teacher's internal representation as well as the task-specific soft logics to guide the distillation process. Generally, knowledge distillation can have the following information flow. So you have the teacher. Now you can continue pre-training the teacher model for language model fine-tuning on task-specific unlabeled data. This makes it aware of the domain semantics and vocabulary for the given task. Now, given some amount of labeled data, you can fine-tune the teacher model for the downstream task and use it to produce logics and representations on the unlabeled data. This gives us the augmented data that we can use to transfer knowledge to the student model via soft training. In this work, we focus on multilingual NER as a primary task. We are given a number of sentences in different languages. Each sentence is a sequence of tokens. We want to associate a tag to each token. We pose this as a sequence labeling task or a span detection task. In this, we want to associate span boundaries in terms of markers like beginning of the span, intermediate token in the span, or out of span boundary. And we want to develop a single model to do this task that works seamlessly across all the different languages. For this, we need a multilingual encoder. In this work, we adopt Multilingual BERT as a teacher model that is pre-trained on 100 full languages in Wikipedia. Also note that Multilingual BERT does not use any language ID for pre-training. Knowledge distillation in our case works on two different segments of the data. First, you have task-specific labeled data on which you can find-tune the student model. The student is a three-layer neural network consisting of the word embedding layer, the RNN layer, and the final feed-forward layer. Instead of the RNN student, you can also use the transformer as a student, and there are experiments in the paper. The other part of knowledge distillation operates over the task-specific unlabeled data. For each sequence, for each token, we want to make the student model produce logics that matches the teacher's predictions. So we want to optimize for the mean squared error loss between the corresponding logics of the teacher and the student. We also want to leverage the teacher's internal hidden representations to guide the student model. To this end, we want to optimize for the representation loss of the student model coming from the final layer, as well as the representation coming from some hidden internal layer of the teacher model. So we have three different loss functions. We have the cross-entropy loss defined over the labeled data, and the representation loss and logic loss coming from the unlabeled data. Now we can use hyperparameter to combine them. However, this is susceptible to the choice of the hyperparameters, which requires an extensive search. We can also adopt a stage-wise optimization scheme in which we first optimize for the more general representation loss and gradually move towards optimizing for the more task-specific loss. However, there are some challenges related to catastrophic forgetting, where the model forgets information that it learned in the earlier stages or tasks. There are several approaches that have been proposed to mitigate this, ranging from progressively freezing different layers, lowering the learning rate of certain layers in the neural network, and other regularization techniques. In this work, we use a combination of freezing and unfreezing of the neural network layers with a cosine learning rate scheduler to give us a better optimization schedule. We perform our experiments on the wiki-ANN dataset over 41 languages for identifying named entities like person, organization, and location. We adopt multilingual BERT as our teacher model, which is jointly fine-tuned from the labeled data from all the languages. MBERT single is fine-tuned from the labeled data for each language independently. XtremeDistil is our framework, and we also compare against the MMNER work from last year's ACL. Here we observe that the different models obtain the same performance trajectory in terms of the F1 score for different languages. This is interesting because these models use different encoders in terms of transformers and RNNs. We also have a lot of experiments related to classification. Please refer to our paper for details. To summarize performance for XtremeDistil for NER, we observe that it has a 95% performance match with MBERT while obtaining 35x parameter compression and over 51x latency speedup. Moreover, we have a single model that operates across all the different languages. And as I mentioned before, we do not use any language ID either during the distillation phase or the pre-training phase. And it can be easily extended to other languages as long as you have unlabeled data for the same. Here we show the trade-off between parameter compression and F1 score. Obviously, as you compress a model more and more, you lose the performance in terms of F1 score. In terms of regulating the parameter compression, you can either reduce the word embedding dimension or the number of hidden states of the RNN. Here we choose a configuration which gives us the 95% performance match. One thing to note here is, as you reduce the word embedding dimension, it can lead to massive parameter compression. However, it does not necessarily translate to an inference speedup. The latency is largely contributed by the number of hidden states in the RNN or the number of layers when you are using transformer as a student model. Again, you would want to choose a configuration here that gives the best latency speedup with the parameter compression for the reduced memory footprint for the corresponding F1 score match that you would want. Here we show the progressive improvement in our model as we incorporate more sophisticated features in terms of the logits, as well as the internal representations of the teacher, followed by gradual unfreezing of the neural network layers for better optimization. We also observe that as we increase the amount of unlabeled transfer data, the student model performance improves till a certain point, after which there is diminishing return as you add more data. In general, we observe that unlabeled transfer data is the key to minimizing the performance gap between the student and the teacher model and obtain a great distillation performance. We note that as we use higher layers of the teacher to guide the student model, it is increasingly difficult for the student, for a shallow student model to mimic the deep layers of the teacher. In general, if you are using a 12-layer transformer, then the information coming from the center of the layer, for example, the 6th or 7th layer, works quite well in practice to guide the student model for distillation. We also observe that random initialization of the word embedding matrix works quite well in practice. You can, of course, do more by using glove and fast text embeddings for pre-trained, in terms of the pre-trained word embeddings. You cannot directly use the fine-tuned multilingual BERT word embeddings because of a large number of parameters coming from the 700-dimensional word embedding dimension. However, we can use singular value decomposition for dimensionality reduction and still use the fine-tuned MBERT word embeddings. This gives us somewhat performance boost by reducing the noise. To summarize, in this work, we study various distillation aspects ranging from different kinds of features in terms of soft logits and internal representations, as well as the trade-off between parameter compression, latency speedup, and the F1 score. We showcase our model performance configuration with 95% performance match and 35x parameter compression and 51x latency speedup. We also have a single model across all the languages and can be easily extended to other languages since we do not use a language ID either for distillation or for the pre-training phase. This model is already in production for several of the scenarios in Microsoft. To give you some insight into why such a framework would be hugely useful in the deployment environment, Consider the following hypothetical enterprise scenario where you have 100 million users. Each user contributes 10 queries per day. In a 52-week year, you would have 5 work days per week. You can multiply all of these numbers to obtain the expected cost of deploying such a model after factoring in the GPU cost per hour and the 100 millisecond latency for query processing by the BERT model. Our model reduces this latency to 2 milliseconds for the query processing, and therefore this contributes to $15 million per year savings for deployment. This comes with this 95% performance match and the reduced compression for the memory footprint, as well as the latency speed up for fast inference. Our code and resources are available in the following link. Thanks a lot for your attention.